Well, the amount of equivalent resistance, and I'll prove this to you more formally in just a second, if I want to get the total resistance of my circuit, in this case, I just add them. So the amount of resistance in the circuit is just the sum of the two. You have to go through both of them, of course, overall, right? So let me go over here. Let me skip a line for reasons that will become apparent shortly. But I want to talk about that the equivalent resistance, how do you get it in a series circuit? You just basically sum the resistors in your chain. You guys know the summation symbol from math class? Yes? You just add them up. So in my case, that's 3 ohms. So the equivalent resistance of having a 1 ohm and then a 2 ohm resistor is really having just one 3 ohm resistor. I guess I should mention too that if all of your resistors are equal, you have R plus R plus R plus R dot dot dot, and you have n of them, of course then you just multiply the resistance of one by how many you have. So if you have identical resistors, your equivalent resistance will be just the number you have times the resistance of each. Now, I know that's so obvious, so why would I bother putting that? Well, it's always because there's something on the parallel side that we can compare to. Okay. So that's the resistance. Now let's get to the voltage. So the voltage, now we have a distinct journey with a middle step. Here we have our highest voltage equipotential region. It's the high voltage terminal of the battery and that contiguous piece of wire that's connected to it. That's the highest voltage, and I'll call that region A. And then I also have the lowest voltage region in the circuit, which again is extended quite a ways by this wire, and I'll call that C. But there will be a middle step. There will be a voltage here. There's a piece of wire that connects this. This will be an equipotential region. So we have a top plateau at the very top and very bottom, but there's a middle step. Now, how do I know there's a middle step? Well, I know that current flows through both of these. So the only way that current would bother to flow through this obstruction from A to B is when it has a reward for doing that, right? Current is not going to flow because you want it to. It needs to have that reward. So it flows from A to B because B is lower voltage than A. Well, that would be the end of the story. But the reason why the current keeps going from B to C is, of course, because C is even lower voltage than B, right? So the only way that the current will bother to go through there is if it continuously has a reward for going to lower voltage. So I like to draw this as kind of what I call a voltage waterfall. Voltage waterfall. Or I think some of the homework solutions are referred to as a voltage schematic, which I think is a much more boring name, so now they're called voltage waterfalls. Basically the way they work is that the higher you are on the page, the higher the voltage is. So think of it like this. The battery kind of functions like a pump, and it raises charges to higher voltage, and then they trickle back down to lower voltage through the two resistors. First, it drops a little bit through the first resistor, and then it drops the rest through the second. So again, we're thinking of these as equipotential plateaus, and the way that you drop between them, so you drop from region A to region B through resistor 1, and then you have from B to C through resistor 2. These kind of voltage waterfalls are extremely helpful for organizing your information. I highly recommend them. One of the things it really shields you from is cosmetic differences in the circuit that don't matter. Okay? I'm going to draw some circuits that look pretty funky a little bit later, but this will keep you from being worried about it. For instance, if R2, this second resistor, was here, it wouldn't matter if it was down here. It would still segment this up into three equipotentials. Okay? In fact, what we have here is that you have the entire voltage drop that's set by the battery from top to bottom happens in a two-step process. This, by the way, is my opportunity to prove to you that this equivalent resistance formula is correct, because for here, I'll substitute I total times R equivalent. That's from over here. And over here, I can also substitute in Ohm's law for each individual resistor. V1 is I1 R1, and V2 is I2 R2. So all of these currents are the same current, so it's a little silly. We already said that the current is the same in a series, and so look at what's left. R equivalent is R1 plus R2. So we found the resistance formula, the way for determining equivalent resistance, is indeed correct. Okay, so as far as the voltage goes, you might say, are the voltage drops equal? This is 12 volts. Are these each 6 and 6? Well, it turns out that does not occur. The voltage drops are not the same across each resistor. Let me try to explain to you why that is. Remember, we have a common current that is flowing through the whole thing. There are no forks in this river, so there's a common current. But not everything along the path is equally difficult to get through, right? We have a small obstruction and a big obstruction. Well, what does that mean? It means that if we have a big obstruction, we need to give a bigger reward to keep the whole thing moving more easily. So here, we're going to have less voltage drop, and here, we're going to have more voltage drop. They have to add up to the battery EMF, 12 volts from top to bottom, but that does not mean it splits evenly. Here's my best analogy for how to think about this. So instead of a line of charge moving through, let's say we have a line of kids. Okay? We want to keep a line of kids moving along smoothly, calm, nice, easy current. They've put two obstructions in their way. So there'll be two things that they have to do. This resistance will be eating a piece of broccoli. So that's resistance because kids don't like broccoli, right? And then this one will be getting their vaccine or something like that. So also kids really don't like shots. So we have a small obstruction, broccoli, big obstruction, vaccine, okay? So if we were to strategize on how we could keep all the kids from backing up and avoiding the shot, we have to proportion our rewards accordingly. So if you eat your piece of broccoli, we'll give you a lollipop, okay? And if you have your vaccinations, we'll take you to Disneyland, okay? So that's what we're doing here. We proportion up the rewards according to the resistances. That's what keeps the current moving smoothly. So if we calculate here, we're going to find that the biggest resistances have the biggest rewards. So I like to think of the large resistances as kind of like the bottlenecks. So these are like the bottlenecks, so to speak. Bottleneck. You have to go through everything, right? That's the whole deal with this series, is you have to go through everything, one followed by the next. And it means that the biggest resistances are the things you're going to have to pay the most mind. Okay, so they have the biggest rewards as well. Let's calculate what those are. Let's see, where do I have space? So I'll go up here. So V1 equals I1 times R1. So what is the current? The current we calculated. Did we calculate the current? I guess we didn't. We have to calculate that. All right. The total current is going to be the voltage, 12 volts, divided by the equivalent resistance, which is 3 ohms. So that's 4 amps. So that's how much current is drawn now. Remember, I used the same 2 resistors as before, connected to the same battery. When we connected this resistor alone, we got 12 amps. When we connected this other resistor alone, we got 6 amps. Now we have only 4 amps. Why is that? Why is the current so low?
So you have to go through both.
The resistance is bigger, right? Now you have to go through both of them, not just one. So the current tends to be very low. The equivalent resistance is very high, and so the total current is very low. That's what happens when you put a big obstruction in the way. The current goes down to a smaller value. Okay, so there's the current. Let's use that now. That current is the same through every element. So for resistor 1, it has 4 amps going through it. It's a 1 ohm, so we get 4 volts. And then for the other one, V2 equals I2R2. Also 4 amps going through that, but it's a 2 ohm obstruction. So we get 8 volts there. What's 4 plus 8? 12, exactly. So we have our 12 volt journey from top to bottom, and we drop 4 volts across the smaller resistance, and we drop 8 volts through the second. So the total journey is 12 volts. It's split up with the smaller voltage drop across the smaller resistor and the larger voltage drop across the larger resistor. Okay? In fact, you might go even further and just instead of just saying this is less and this is more, we could say something more fancy like this is twice the resistance, so it's going to be twice the voltage drop. And it is. If you get really good at this, you can just write down what the voltage drops are. You just look at this and go, oh, this is 12. So these 2 combined will be 12, and this has to be twice the other because it's twice the resistance. So what's something plus twice that something equals 12? Oh, okay, it's 4 and 8. Done. So those are the kind of things where you get really comfortable with this stuff. You don't need to work it out quite so much in detail. Okay, so that's the voltage. So in a series circuit, the current is the same, no forks, but the voltage drops are not the same. The big resistors, the bottlenecks, get the largest voltage drops. Okay. Now before I hook it up, of course, the last order of business is to calculate the power because the power is the only thing we can visualize because I don't have any measurement devices to confirm any of the other values. So let's calculate that power dissipation real quick. And the power dissipation, this is where I can show you why it's nice to have 3 different forms of the power law to pick from. I'm going to suggest that in a series circuit, you might want to use this one. Now, it's not that the other ones are wrong, but that one's the one that is the hardest to go wrong with. There's no way to plug in a wrong current because there's only one current. Whereas if you're plugging in for voltage, you got to be really careful because there are 3 different voltages here. There's 12 volts, 4 volts, and 8 volts. If you plug in the right one, you'll be just fine. But if you plug in the wrong one, you'll get the wrong answer. So why use an equation which is more potential for going wrong? Let's just use the one that is your friend. Okay? So let's calculate. P equals I squared times R. It's nice to see here, if everything has the same current, we notice that the power is proportional to R. Which means that if the resistance is larger, what is that going to mean about the power dissipation? It's larger. Okay? So if you have a series chain of resistors, all the action is at the big resistors. The bottleneck, so to speak. The biggest resistors have the biggest voltage drop. They have the largest power dissipation. They will be the brightest of the bunch. Okay? That's where all the action is in a series circuit. It is in the large resistors. The larger it is, the more is going on there. So let's go ahead and calculate for what we get. So I can do P1 equals I1 squared times R1. So a current we found was 4 amps, and the resistor is 1 ohm, so we get 16 watts. Then we do it for the other resistor. P2 is I2 squared R2. There it is. Current's the same. I can't mess that up. Just got to plug in the right resistance. And I get 32 watts. It's not like I have to use that equation, so I do want to make that clear. If I use V2 squared over R2, that would give me the right answer. But what's V2? Is it 12? 12 volts? Is it 4 volts? It's 8 volts. So 8 volts squared divided by 2 ohms is also 32. It's just a lot easier to go wrong by plugging in the wrong voltage. Most common mistake is plugging in the battery voltage. That's not the voltage drop across that resistor. That's the whole voltage drop. Okay, so we do find what we predicted. The large resistor has more power dissipation. In fact, we find that since this is twice the resistance, it also has twice the power dissipation. So what are we looking for in the demo? So in the demo that I'm just about to do, here's what we're looking for. First, we expect that the larger resistance is brighter than the other one. So that's one thing we're looking for when we hook this up. That's just a relative thing, right? Which one of the two is brighter than the other? But it might also be informative to compare both of their brightnesses to what it was when they were connected individually. So when we connected up this 1 ohm resistor, it was 144 watts, but now it's only 16. This 2 ohm resistor, when it was connected alone, dissipated 72 watts, now it's 32. So what we should see is that they are both less bright than when connected alone. So both are less bright significantly than when connected alone. These are the things we're looking for, all right? And I'm going to hook this up, and hopefully you will see that that is the case. So first, let me throw in the resistance, the R. Again, take a mental snapshot of how bright that is. That's my first resistor. Then let me just connect this one alone. Again, we're just refreshing your memory on how bright it is when it's alone, like that. And now let me connect them in series. So in order to do this, I have to move these apart a little bit so I can make the charges go through both of them in a row. So one, and then got to go through the other. So this is my series. Doesn't matter which order I put them in, because the entire system will sense how much resistance is in the way. Now it's going to be all of this. So we've chopped this up into 3 distinct equipotential regions. There's the highest voltage over here. Okay, and that's the region A as I've labeled it. We have the lowest voltage over here, that's region C. And then this whole middle section is the middle step. So charges will drop voltage going from here to here, and then also from here to here. Okay, so let's connect it and turn on the juice. And so, first of all, we do see that the larger resistance in the chain is brighter. I think that's pretty clear. Yes? So this 2R is twice as bright as this one. Okay? So this is the bottleneck in the system, right? This is the big resistor. All the action is here. More voltage drop, more power dissipation. Okay? We also obviously see that both of them are far less bright than they would if connected alone. And that makes sense, because this is a much bigger obstruction, so the current going through here is very low. So the current going through here is very low, and they've split the voltage drop now, so neither of them even have the entire drop among them, just alone. So when you decrease both the voltage drop, because you're sharing it with another resistor, and the current overall is smaller because you have all this resistance in the way, it's no wonder that both of them are less bright than they were when connected alone. Okay? So that's the series circuit. Are there any questions? Yeah.
You said when R increases, P increases.
Yes.
In series.
Right. So comparing these to the since this was a more resistance, it was twice. It was more power as well.
Are you talking about the overall resistance or just individual resistance?
So if you want to calculate the power output of one resistor, you have to put in that resistor's stuff only. Right? So the power dissipated by one resistor is how much current flows through it and its own resistance, not the whole thing. Is that answer your question?
Power, it's the power dissipated, or?
Yeah, that's what power is. Power dissipated. So it's
Even though
energy.
it's brightness, it's dissipated?
Well, sure, it's dissipated out into the environment. That's how you can see it, right? It's not in the system as electrical potential energy. It's being sent, dissipated out to the environment. It's not coming back, right? So it's kind of like friction. It's basically gone. Did that answer your question? I think. So make sure you distinguish between these two things, right? There's the power dissipation that we're comparing these two to each other. So in this case, this resistor is brighter than this one. But they are both less bright than when they were connected alone. So those are two different considerations.
But when you use that,
This?
yes.
This is referring to an individual resistor. So when I say R, I say one resistance in the, we have a bunch of resistors in the chain, and the larger one in the chain will dissipate more power. So if we have like 10 resistors in a row, whichever one resistance in that chain is the highest resistance is going to be the brightest. Okay, so I think that's all the time we have today. I'm going to start with this on the board next time because we're going to find that it's very much a modified version of each row here is what appears in the parallel circuit. So I'll connect that up and do the calculations next time.